if I have two vectors, I'm going to say that one goes in this direction and the second vector goes in this direction. Okay? I can't just add those as is. I've got to actually see how they fit together, okay, in order to determine what a resultant is. So you're going to end up having to move, if we call this vector 2 over here, and we call this one vector 1 over here, you know, either or. You could move vector 1 to the end of vector 2, or you could move vector 2 to the end of vector 1. In theory, it should give you the same answer. Okay, so we're going to go with moving vector 2. So when you want to do something graphically, you've got to actually move these guys. All right, and you've got to place the tail of the second vector on the tip of the first. You see that? Because each individual vector is going to have its own little origin. Okay, so it's like saying, if I move this over here, it's like saying that for vector 1, we have this little origin, because that vector has a magnitude and a direction. The magnitude is the length of the arrow, right? Every vector has a magnitude. It has an amount. Yeah? Every vector is also going to have a direction. It's going to start from 0 and then go to wherever the line is. That is the theta. When we start from 0 and go to wherever the line is, that is the theta. Okay? So, vector number 2 is also going to have its own little magnitude and direction. It's going to have its own little quadrant. And you can tell by looking at vector 2 that it is in what quadrant? It's in quadrant number 1, right? Because it's kind of got a little bit of an elevation and it's pointed towards the right, right? What quadrant is vector 1 in? It's in the second quadrant, or quadrant 2, right? So now that we've placed these vectors tip to tail, and we've aligned that second vector, because the second vector hasn't moved, nor has the first one. They still have the direction and the magnitude that they started off with. Now, once they're placed tip to tail, we can actually figure out where the resultant goes. And when we add a resultant, okay, when we add a resultant, we are looking for starting at the starting point down here and ending at the ending point of this addition. Okay, so we start down here and we move towards our tip. Okay? So in order to actually determine what your resultant vector is, okay, so this would be V1, because it's got a magnitude and a direction. V2 gets a little hat here, because it's got a magnitude, so a length of the arrow, and it's got an angle of elevation. So it's got a direction. Now, V3, or I'm going to call it VR, is the sum of both those vectors. It too will have a magnitude. It too will have a direction. You can measure the magnitude with a ruler. You can measure the direction with a protractor. Okay? So there is a way to actually properly draw this kind of addition. Now, if I provided actual magnitudes and directions for these two vectors, you could use the component method to solve it. And then you can see if they add up, kind of like what we did in the last problem. I will expect you to draw out what it is you calculate. Okay, you're going to have to draw something to scale. We'll practice it. It's actually a fun problem to kind of answer because you get to see if your work is right or not. And it feels pretty good when it actually lines up. Okay, when you're like, oh, I got it right. Nice. Okay, so So if we change the order, we put the second vector down first, and then we add that first vector on second, we're still starting at this point and getting, now I didn't draw that perfectly, but you're getting the exact same resultant. Do you see that? Okay, so maybe you can rewind a little bit on the video and then move it up. It should be the exact same thing. So in theory, no, it doesn't matter. Ideally, if you're given a problem, you will draw the vectors in the order that they're given. Okay, so if it says that a driver drives down the road, down an easterly road for 10 kilometers and then veers northeast for another 15 kilometers and then drives, west for 20 kilometers, you will follow that as vector 1, vector 2, and vector 3. Does that make sense? Okay. So the next thing we're going to tackle is the concept of why, when we're doing the component method, that looking for, because we know that the resultant vector is going to be equal to the sum of all the x components plus all the y components, right? We know this. Now, we also know that in order to determine what an x component is and a y component is of a vector, all we need are the vector's magnitude, right? Its number, and we need its direction, whatever angle it's at. Now, the reason that Vx is equal to the magnitude of the vector times the cos of the angle dates back to trigonometry. SOHCAHTOA, what does that mean? Do you know what that means? You've all covered that, correct? Yeah. So, SOHCAHTOA, right? Sine, cos, tan. Yes? So if I say that Vx is going to be the cos of that angle, if I give you, a vector, all right, and I say that it's got a magnitude of whatever, it's not important. But if I tell you what the x component is here, let's draw it out. The x component is right here. And if we have our theta here, I've got the adjacent angle over the hypotenuse. Cos. Did a light go on for anyone? Similarly, if I look at, just going to move that over. Do you guys have a better understanding of that now? Yeah? Okay. What time do we have? Bingo, bango, the bell's going to ring. Next class. No, it's paused. Oh.